Hi, my name is Akash Bhatt, and this is my presentation on Lab 4 regarding circuits and capacitors. In this lab, we explored how circuits work and which elements are required to make sure they function properly. We were tasked with predicting the behavior of circuits containing resistors in series and parallel using multimeters to measure conventional current and potential difference. We were also tasked with examining the behavior of ohmic resistors and capacitors. In this lab, we used 4 different scientific concepts that we have learned this year. Where we used the loop rule, which means that across any loop in a circuit, the change in voltage must be 0 overall. The node rule, which claims that the sum of the current flowing into a junction must equal the sum of the current flowing out of that same junction, such as when the current splits into 2 wires. Ohm's law, which requires that voltage equals the resistance times the current in a circuit, as well as capacitance, which claims that the voltage must equal the charge over the capacitance for a capacitor. The first activity we had to complete was to create a series circuit with 2 resistors, one of 47 and one of 100 ohms, along with 2 batteries of 1.5 volts each. To predict the current at both the top wire and the bottom wire, we used V equals IR to discover that the predicted current should be 0.0204 amps. Using the ammeter located in the lab, we were able to discover that this prediction was correct, and the current flowing through the top and bottom wires was both 0.02 amps. When a section of the wire was replaced with a voltmeter, we were able to see that the change in voltage between the points on the wires was -3 because the circuit was no longer closed, and therefore no current was flowing through. Therefore, the ammeter reading on the top of the circuit was also 0. This is because, as previously discussed, there is no current running through the wire. Using a voltmeter to measure the change in voltage over different parts of the circuit allowed us to confirm the loop rule, where we were able to add up all the voltages across the circuit and find out that the final value was 0. Here is the level of voltage at different points across the circuit in the series circuit discussed previously. During this first part of the lab regarding a series circuit, we were able to make some observations. Although the voltmeter alters the circuit, the reading of the ammeter doesn't change because the voltmeter has a very high resistance, so no current flows through it. The ammeter reading does not change when the voltmeter is placed around the 100 ohm resistor because of this concept. However, when an ammeter is placed in parallel with the other resistor, the current in the circuit changes because no current travels through the part of the wire with a resistor in it, reducing the overall current in the circuit. Using the potential difference measurements that we made 3 slides ago, we were able to determine what the value of the resistor should have been, and these were our calculations. Compared to the actual answers, these answers are pretty close. For the next part of the lab, we needed to create an RC circuit, which includes both resistors and capacitors, to explore how they function. We used a battery, a 10 ohm light bulb, a 20 ohm light bulb, and a capacitor with 0.2 farads capacitance. In this first series of images, you can see how charge accumulates on the capacitor as time goes along when connected with the battery. At first, the light bulb turns on as current is running through the system, and then the light bulb shuts off after the current becomes very low as the capacitor is fully charged. After the battery is removed, the capacitor begins discharging. During this phase, as you can see with these 3 images, the light bulb turns on as the current starts again, but once the capacitor is fully discharged, the light bulb turns back off. For the 10 ohm light bulb to completely discharge, it took 4.61 seconds, and for the 20 ohm light bulb, it was almost double that amount of time. The last activity we were tasked with completing was to find the RC time constant for a capacitor in a circuit. To do this, we use a light bulb which has 30 ohms of resistance as well as a capacitor with 0.2 farads of capacitance. Here are my data points for measuring how fast the capacitor was charging. I have data points for the time, every 3 seconds for the first 60 seconds, what the voltage was at that point in time, and then the natural log of the current voltage over the initial voltage, and that data is graphed with a line of best fit shown to the right. Using the experimental values, we were able to calculate that the RC time constant was 6.59, as we used a slope and did -1 over RC and found that time constant. Theoretically, however, this time constant should have been 6, because to calculate the time constant, you must multiply the resistance by the capacitance. Using the two values used in the circuit, this value should have been 6. If we had used an actual ammeter, it would not have had zero resistance. This is because no object ever truly has zero resistance. Therefore, the ammeter would take up a small amount of the voltage from the battery. Thank you for watching. This has been my presentation on Lab 4.